Good evening. Today we are going to see the problem that is on eccentric footing. So already we have seen problem that is on axially loaded footing. Now we are with eccentric footing. So we have problem design a footing for a column carrying an ultimate. Now values are given ultimate. So we have this value given 600 kilonewton, which is axial load, and moment is given 200 kilonewton meter. About an axis bisecting the depth of column at its base. The size of the column is 300 millimeter by 450 millimeter. The SBC of sile is 150 kilonewton per meter square. Use M20 and Fe 500. So now the first step we have different actually. So now first given data Pu 600 kilonewton, Mu 200 kilonewton meter. Ultimate SBC 1.5 into 150, 225 kilonewton per meter square. Sorry, M20. So these values actually we have this as M25 and Fe 500. So M25, Fe 500. Then we have RU max. So 0.36 FCK KU max 1 minus 0.42 KU max. So this value is correct. We have used that is of 500. So 0.46. This is also 0.46. And then from this we will get RU max 2.67 Newton per mm square. Steps we have same whatever we have, that is for axial loaded footing. Area required, that is pad footing we have seen. Total load on footing upon ultimate SBC. Total load we know. We have total load that is 1.1 into 600. So 1.1 means we are considering 10%, that is self weight. So 600 we have load on column and 10% we have that is self weight, and it becomes 660. And therefore we have taken it as 660 upon 225, that is 2.93 meters square. So now we have to consider area which is around 1.6 times, that is area required, because moment also accommodate in that one, and therefore we will have to increase the area. So I have taken size of footing. Now we will have E equal to M by P. So that is 200 upon 600, 0.333 M. And then we have LF equal to 6 into E. Now we have three types of this footing. So we have first, that is LF greater than 6E. Second, we have LF equal to 6E. And third, we have LF that is less than 6E. In this, our whole base is in compression. In this, we have at one end value 0, and another we have compression, and here we have tension and compression. If I will draw the diagram, then we have diagram of stress in this fashion. So we have both side compression. So that will be first case. Then second we have that is 0 on other end. So we are being in this fashion. And third we have that is tension and compression. So we may have little bit tension, that is depending upon your grade of concrete. Now from where these values comes actually, so we have stress equal to P by A. So if you remember that is combined loading in MOS, then we have P by A minus M by I into Y. And that I by Y is considered as Z. So we have P by A, M will be written, PU I will mention better. This will be MU. So MU upon MU I can write PU into E upon Z. Now that Pu, so this value if I will say equal to 0, then we have Pu upon B into D. and that is equal to PU into E upon BD square by 6. And then in this PU get cancelled, BD get cancelled, and then we have ED that is equal to D that is equal to 6 into E, and B and D we have that is width and depth of footing, and therefore we are considering this value 6E if value 0, if greater then we have values in this fashion. Here we will consider 6E and we will provide greater so that we are with this condition. So now we have 2 meters, we will provide it as 3.5 meter. I already mentioned we have to increase area, that is about 1.6 times. And why? Because we have moment is also there, and to accommodate that moment we have this will be 3.5 meter, and BF we will put it as 1.3 meters. So now next we have area provided 4.2 meters square. So you can see 3 into 1.6. So around it comes 4.8. So I have provided 4.2. So 1.6, that is maximum value we are considering. So it comes 4.2 meters square. So you can increase and then you can go higher side. I kept it like this. So now we have next bearing pressure. So just we have seen formula. We have P by A plus minus M by Z. Section modulus is Z. And I have substituted value. We have 600. And this is width of the footing. And this is depth of the footing. And here we have BF into DF square by 6. So that we have already seen. We have Z is equal to I by Y. I we have BF into DF cube by 12, and Y we have DF by 2. And from this we will get it as BF into DF square by 6. And that value we are considering over here. From this we will get 600 upon 3.5 into 1.3, 131.86. And second, plus we have taken first, which I have mentioned, maximum bearing pressure. 207.21 kilonewton per meter square. Values please check once, less than 225. And then minimum bearing pressure 131.86 minus 75.35 once plus another minus 56.51 kilonewton per meter square, and now greater than 0. So whole base is in compression. Now you can draw this diagram. So we have bearing pressure in this fashion 207.21 kilonewton per meter square. So we have this value kilonewton per meter square, and this value also kilonewton per meter square. Then we can go next, that is bending moment. We have to find at face of the section. It will act as cantilever portion. So we have bending moment. If we will calculate, then we have that will be as a cantilever. Now what will be cantilever portion? We have total length of footing is 3.5 meter minus we have depth of column 0.45, and then we will have this will be 3.05. So half on left side and half on right side. So if we will divide this by 2, then we have value 1. So that I have mentioned here, we have 1.525 meters. So that is beyond face of the column. So we have this value. Now we will have pressure intensity at this. Now how we will calculate this? So now this is most important. I have mentioned here. So if I will draw this diagram on this side, so we are in this fashion. So now we are converting into rectangle and triangle. So we have this triangle 56, rectangle 56.51. So we have 56.51 plus. Now we have this difference. So 207.21 minus 56.21. Now divided by 3.5. So we will have this triangle. Now where we require this value? So we have distance from this side is 1.525. Total is 3.5. So for considering triangle, I have considered 3.5 minus 1.525. And from this, we will get this ordinate. And then we will add this ordinate 56.21, which I mentioned over here. I will get value at 1.525, and I got this value 99.21. Add 56.21, we have 155.72 kilonewton per meter square. So now we have bending moment at the face of the column. So we have 155.72, 207.21. And now we have to find bending moment at face of the column. Now we have to divide it into two parts. One we have that is rectangle, and another we have that is triangle. So for UDL, we have rectangle WL square by 2, and for triangle, we have to take total area, total load, and then we have to take moment about the base. Now you can see first we have bending moment at face of the column. Now due to UDL, 155.72 into width, 1.3. So now the multiplying width, this becomes my UDL into 1.1525 square by 2. So this is bending moment due to UDL. Means if I will draw it separately, then we are in this fashion. So this is UDL and is fixed at this. So we have value of this UDL is 155. So this 155.72 into 1.3. And we have this distance 1.525. And then we have triangle. In this triangle, we have this value that is equal to 207.21. I have mentioned there minus 155.72. You can see over here. So area of triangle 1/2, base we have 1.525 and height 207.21 minus 155.72, and this is width, and this will act at centroid. So at centroid means we have 1/3 from here. So automatically we have 2/3 from fixed end, and therefore we have 2 by 3 into 1.525, and we will get bending moment at face of column that is equal to 275.3 kilonewton meter. So now we have in y direction. Now in y direction, we have to take average stress. So we have average stress 207.21 plus 155.72 upon 2 into 3.5 into 2.285. Now how we will get 0.285? So we have this will be my footing. And we have column on this side. So now length we have 1.35. Sorry, 1.3. And then we have this as 0.3. And then we have cy square. So we have 1.3 minus 0.3, and then this will be 0.5. And we have this also 0.5. So that is a mistake over here. So we have actually this will be 0.5 square. That is bending moment at face of the column. And then we can calculate this value. So just I have calculated that is actually considering 0.285. So just I will calculate it. 21 plus 155.72 divided by 2 multiply by 3.5 into 0.5 square, and it comes 158.78. So it will be 158.78. 78 kilonewton meter. Now this will be, we have multiplied this by width. and then this becomes UDL on this side. And from this we will get that is 158.78 kilonewton meter. So this is in y direction, above we have in x direction. So now we have next depth from bending moment. So we have mu upon Ru into BD square. And then we will get this value 281.63. I have not taken second one because in that case, this value is again, so this is not 1.3 actually. So we have again, this will be 1300. In second case, this width will be 3500. So 2.61 into B, D square should not be there. Mu upon Ru into B. And in y direction, this B will be 3500. So this automatically comes less. So we have taken 281.63. Then we have provided overall depth 500 mm. Effective depth as 440 millimeter. Dy becomes 430, assuming 10 millimeter diameter bars. Then we have check depth for two-way shear. So now we are in this fashion. So in two-way shear, we know we are going to consider distance beyond face of the column, that is dy by 2. Dy we have 0.43 and by 2. So we have this value, that is 0.215 meters. So we have 0.45, 0.215, 0.215, 0.3, 0.215, 0.215. So same steps we have perimeter at critical section. In the same way, whatever we have used, that is for pad footing axially loaded column. So we have 2 into, we can calculate this and we have this value that is equal to 3.22 meter. Hey, dy by 2 plus 0.45 plus 0.215 plus 0.215, 0.3, 0.215 into 2. So 3.22 meters. Multiplied by dy we have 0.43, so 1.38 meters square. Then we know we have to find shear at critical section, same formula greater than 1. So consider 1. Shear at critical section we have 0.25 root FCK. So we have 1.25 Newton per mm square. Then shear strength at critical section. So area 1.38 into 10 raised to 6 because that is meter square converted into millimeter square into 1.25. 1725 kilonewton at critical section shear strength. Now shear force we know WU LF into BF minus area at critical section. Now we have that is bearing pressure. So we will consider that is WU as PU upon area of footing and we have 131.78. And this will be area of footing minus this will be area at critical section. And from this we will get value as 515.3 kilonewton less than 1725 kilonewton. Then we have step 6 reinforcement. So we have same formula, put value 275.3. Then we have this value 1519.83 mm square. Now in this in IS that AST minimum for footing is given 0.85 BD upon F5 and we have 972 mm square less than 1519. So we will provide 8 bars of 16 mm diameter along X direction. Now ASTY, actually I made mistake in this one. So this footing, this moment we have to consider, that is 158.78. So just put MUY 158.78. So in 1 minute I will calculate 158.78 to the power 6 divided by 25 into 3500 into 440 square. 1 minus answer, root of answer 1 minus 4.6 into 158.78 to the power 6 divided by 25 into 3500. Width we have to take 3500 square. So 1 minus answer, root of answer 1 minus answer again into 0.5 into 25 upon 500 into 3500 into 440. So it comes 839.13. So 839.13. So I will correct it. 839.13 millimeters square. Now keep in mind, in MUY, you have to consider B as 3500 millimeters. So in both, here also you have to change it, here also you have to change it. Now AST minimum, we have that value, that is 2618 mm square, and provide 13 bars of 16 mm diameter along X direction. Now step 7, check depth for one way shear about X axis. So we have dy from face of the column, and this value comes 1.085. Now I have calculated this value, calculated this value 192.35, that is at 1.085, and we have, this will be stress diagram, bearing stress diagram. Now we will have design shear VUD. So we have taken average. We know how we will calculate it. So if you remember, then we will have value in this fashion. And we have column. So we are considering at D, and this we have to consider. And therefore, we have this value 1.085. So we have to find shear stress at 1.085, and then we have VUD design shear. So 1.085 into 1.3. So this will be area, and stress we have this one. And from this we will get value 281.79 kilonewton. Percentage reinforcement 0.28. So we have table 19, which will give us tau UC 0.38. I have made calculations over here. So we have this calculation. I will just show it. 0.36 plus 0.49 minus 0.36 upon difference of the two, which will be 0.25, and multiply by 0.28 minus 0.25, and we will get this value of tau UC. And then we have this value, that is 217, less than this one. Now do not increase depth, increase reinforcement. And I have increased reinforcement, that is to 14 bars from 8 bars. And then we will get percentage reinforcement around 0.49 something. So 0.5 I have taken. And tau UC, for this we will get it as 0.49. So now here we have directly for 0.5, we have this value 0.49 Newton per mm square. And then if we will put it, we will have 280.28 kilonewton. So it is approximately 281.79 kilonewton. So it's okay. So likewise, we have to solve this problem. That is for eccentric moment, is axial load plus eccentric moment. So now we will stop here only. Thank you.